Hello everyone, welcome you all to my YouTube channel Study with Days. Today we shall discuss on polynomials and cyclic code analysis, and also I will quote the advantages of CRC. So I have already in the previous video I have explained about CRC, that is Cyclic Redundancy Check, how the encoder and the decoder works and the process. Here today we will discuss on cyclic code analysis. If we say f of x is a polynomial of binary coefficients, then data word dx is not denoted by dx, code word is denoted by c of x, generated by g of x, syndrome by s of x, and error by e of x. In a cyclic code, if the syndrome is not zero, then it simply means it has an error. That is, one or more bits has been corrupted. If syndrome is zero, then two possible conditions. That is, either it is error free, the message is not been corrupted at all, or there were corrupted bits, but the decoder failed to detect them. The error is not been detected at all. Possibility that one, there is no error at all, or there is an error but we are not able to detect it. So no bit is corrupted, or there are some bit corrupted but we fail to detect them. We want to find the criteria that must be imposed on this generator so that it will detect the errors. The relationship among the sent code word, error, received code word, and the generator is very important. And if we take the receiver code word as sum of the code word and the error, the equation looks something like this. And if we divide, as we say, as I have said in CRC, if we divide that by the generator, then if it ends up with some value, a non-zero value, then it says that it is able to detect the errors. So that is what we are trying to do here. We have tried dividing that with the generator polynomial. So anyways, this will get divided, but whereas this should not get divided if there is an error. Why? Because if it is non-zero, only then the errors are detected. So we work on that term. If it is a single bit error, as I said, so e of x can be equal to x of I. It should be x to the power I, where I is a position of the bit that has been corrupted. Okay. So whatever the generator polynomial we are using, that we have to make sure that that is this x of I should not be divisible by that particular generator. This is very important. Whenever whatever the term we have, that should not be divisible by the generator if in case there is an error. So we have to frame a generator in such a way that after dividing it, we should have a non-zero value. So if g of x has at least two terms, okay, one any term and one especially the term that has coefficient 1 for x to the power of 0, only then this kind of generator can identify all single bit errors. That is, in this example you'll understand better. There is two terms, there is not one term. This is x to the power of 0 and the coefficient of that is 1. So x to the power of 0 coefficient is 1, and at the same time there is more than one term. So on this case, such generator polynomial can identify the single bit errors. But whereas here there is no x plus 1 term at all, so it can detect only first errors at first three position, but from the fourth position it cannot detect. But whereas here, it since this is divisible by everything, no single bit error can be identified. But whereas if you try with this, once you try dividing by with this, you will see it is recurring and it is not divisible at all. So it is a very good example to find this is a generator which can find all single bit errors. So next, coming to two isolated single bit errors. That is, if it is represented like this, if there are two errors at the position j and I, and it is represented by x to the power of j and x to the power of I, and the error is a combination of both, and the distance between them are j minus I. On this note, we have to factorize and you are taking out xi in common. So the equation becomes x to the power of j minus I plus 1 the whole into xi. So we have to make sure that this whole term is not divisible by g of x. Anyways, this should not be divisible by g of x, only then all single bit errors are caught, and we have to make sure that this is also not divisible by g of x. That is the main intention. Only then all the 2 bit isolated errors can be caught. Suppose if I take this j of I as t, okay, and this t can vary from 0 to n minus 1. So the generator cannot divide this, so that all isolated double errors are detected. Next, with this example, we can say this will only find out all single bit errors, so no 2-bit errors can be found. So this is a very poor choice for the generator. Okay. Then with this can also detect, it cannot detect two errors that are 4 position apart. If the distance between those two errors are 4, then it cannot detect. But this is a very good choice. It can detect all isolated 2-bit errors. But whereas this polynomial, this cannot divide any error of the type this if t is less than this on this note. Otherwise, it can detect the rest. But if t is less than 32768, this means the code word with two isolated errors that are next to each other or up to so many bits. That is, either they are next to each other or distance between them are so many bits, then those type of errors cannot be detected with this generator. Next, coming to odd number of errors. Odd number of errors, obviously this, you if you see here, this can detect all single bit errors, it can catch all single bit errors. But factor of this, any generator that has factor of this, for an example, if you see this is nothing but factor of this. If you can see, this into this is this. So this is a factor taken out from this, and this remains. So likewise, if you have a factor of x plus 1, those generator polynomials are very good to detect odd number of errors. Next, coming to bust errors. So here, there are so many errors in between. That is, first error is at the position x to the power of j. In between, there are so many errors at different positions, and the last position is x to the power of I, and the difference between them is x to the power of j minus I. But what is the difference you have to know is, like previous one, what I have said. Here in two isolated bit errors, only two errors are there. But in bust errors, there are many other errors in between this. So our generator should detect the errors. Then that generator should not divide this. This should not be divisible by our generator. We have to make sure that. So if our generator can detect single errors, then it cannot divide x of I. Then we should also worry that those generators should not divide this. Only then it is possible. So if we take this as our generator polynomial, so that this is not divisible, then possibility, that is, here there is r, okay, that is check bits, okay, number of check bits. This, with this, if you compare, three possible things are possible. One, this r is this x of I is less than r or equal to r or greater than r. These are the three possibilities. We're checking into the three. If it is less than r, okay, then remainder can never be zero at all. So all the errors will be detected, all the bust errors will be detected, okay. And if we write, this is nothing but the length of the errors, that is l minus 1. J minus I is nothing but l minus 1, where l is the length of the error. Then it simply means l minus 1 is also less than r, or l is less than r plus 1. This means all the bust errors with the length are smaller than it will be detected. But whereas if in case if it is equal, there are chances that there is an error, but still the syndrome is zero, so the error is undetected. But what is the probability of such undetected error is given by 1 by 2 whole to the power of r minus 1. For an example, if this is the polynomial and this is the r, that is the maximum, you have to take it as r. If r is 14, and so the bus length will be 15, it can slip any undetected error with the probability 1 by 2 whole to the power of 14 minus 1. It is almost 1 in 10,000. Similarly, if it is greater, then same thing, there are chances of undetected errors, and the probability is 1 by 2 whole to the power of r. With the same example, it becomes 1 by 2 whole to the power of 14. It is almost 1 in 16,000 cases. So, CRC is very robust. Here and there, one or two undetected case might happen. Ignoring that, we can still say CRC is the robust error detection scheme. What is the advantages of CRC? CRC can detect all single bit errors except if the generator has more than one term and the coefficient of x to the power of 0 is 1. CRC can detect all double bit errors provided the divisor contains at least three logical ones, and it can also detect odd number of errors if the divisor is a factor of x plus 1. It can also detect the burst errors if the error of length is less than the degree of the polynomial, and it can also detect most of the large burst errors with higher probability. We don't say all the errors are detected, but the probability is too less, and hence we conclude CRC is one amongst the strongest error detection scheme. Thanks for watching.